All right. Hey, everybody. So first day of a new semester. We've got new packets all ready to go, starting chapter 6 today. So starting chapter 6, we're going to be talking about perpendicular bisectors and angle bisectors and circumcenters and incenters and all these different triangle segments that we haven't yet gone over. So to start us off, we're going to do a little bit of a construction just to kind of get us in exploring what exactly perpendicular bisectors and triangles do. So I'm going to have you actually flip over your packet. So you've got a blank space here, and we're going to draw a nice big triangle. So use a straight edge if you've got one. That's going to be, the most effective. But put 3 points on your paper for your triangle vertices. And then connect the dots. And go ahead and label them points A, B, and C. All right. So for each of these segments here, we're going to make a perpendicular bisector. So if you remember way back to first semester when we talked about perpendicular bisectors and we constructed them, remember they're going to cut the segment in half, and they're also going to be perpendicular, meeting up with it at a right angle. And the way that we did this was, like, if I'm going to make the perpendicular bisector of AB, we took our compass and we put one end on A, and we opened it so that it's more than halfway from A to B, but less than the whole thing. So we do that and we save that setting, and then I take it up here and make an arc, and we take it down here and make an arc, and then I turn it around and put the center on B, and I do the same thing with the same size opening. So we put one end up here, and we make an arc that intersects with the arc that we made from A. And then we do the same thing, but down here at this end. And then where they intersect, we connect the dots. Okay, great. So there's one of our perpendicular bisectors. No, it's perpendicular, and it cuts that segment into 2 equal pieces. Cool. We're going to do that with all 3 of these segments. So I'm going to go and do that now with AC right here. So I'm going to open it more than halfway from A to C. And I'm going to make an arc above and an arc below. And then I'm going to do the same thing over here. Make an arc below and an arc above that intersects. And I made this a little bit big, so my straight edge won't quite work. Let me see if I can find a longer one. One sec. Take a book and use that instead. Oh, this one happens to go through B. Doesn't make a huge difference, but that's cool. All right. So that's perpendicular, and it cuts AC into 2 equal pieces. Now we're going to do that with BC, the last one here. So here we go. More than halfway from B to C, but less than the whole distance. Make one arc above the line, one arc on the other side of the line. Turn it around to C. Do the same thing, one arc there, one arc here. And where they connect, we'll connect the dots. All right, so this is perpendicular to BC. and halfway between. Okay, so now we've got all of our perpendicular bisectors drawn, and something we might notice is that all three of the perpendicular bisectors, if we did this correctly, should meet up at one point, which they do right there. That point is called the circumcenter. And that point is equidistant from all three of these vertices, A, B, and C. It's the same distance from here to A as it is from here to B, as it is from here to C. And you can draw those distances if you would like. You can draw that length from the circumcenter to A, the circumcenter to C, the circumcenter to B. And it's called the circumcenter because if I were to make a circle with the center right here, which I'm going to do, I'm going to start here, and I'm going to make it so that the radius is the distance from that center out to one of my vertices. So if I go through and make this circle, oops, which I think I accidentally moved it a little bit, so it didn't quite work. But if I go and make a circle here, and if I did it perfectly, it should end up so that these points are all on the circle. Now I messed up just a little bit, human error, but this point should also be on the circle, showing that this distance is the same between all of these at that circumcenter. Pretty cool. So this distance would be the same as this distance, which would be the same as that distance. Okay, so that's kind of the main idea with perpendicular bisectors and the circumcenter. And if we didn't quite pick up all of that, that's okay. We are going to kind of continue on this theme and talk a little bit more about perpendicular bisectors and the circumcenter theorem and the perpendicular bisector theorem and all that good stuff. So go ahead now, flip in your packet back to the front, and we're going to go to the 6.1 day one notes. 6.1 and 2 kind of go together. So we're going to kind of meld them a little bit and do it in 2 days for both sections. So with that, remembering what a perpendicular bisector is. Well, we just made perpendicular bisectors. We made 3 of them on the back of our packet. So hopefully we remember. But if we don't, it is perpendicular so that means it meets up at 90 to a segment and divides it into 2 equal pieces. Okay. So the perpendicular bisector theorem is listed right here. It says if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So we're going to unpack that a little bit with a picture. So it's saying if we've got, a segment with a perpendicular bisector, so that'll be our segment. This will be our perpendicular bisector. And it's saying that if some point P is on the perpendicular bisector, then it must be the same distance from P to B as it is from P to A. So we're going to draw that as well. So then, if we've got the same picture going, then it must be the same distance from P to A as it is from P to B. So that means if this distance is 5, then this distance is 5. If this distance is 2,000, then this distance is also 2,000. As long as P is on that perpendicular bisector. And we know that it's a perpendicular bisector because of the markings here. We know that this is a right angle and that these 2 pieces are the same. Cool. So then we also have something called the converse of the perpendicular bisector theorem. So it's the same thing, but the other way around. So that says that if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector. So this one's the same thing, but the other way around. So it's saying that if we've got a segment and then some point out here that is the same distance from A as it is from B. So another way to say that would be that PA is equal to PB. Those distances are the same. If that's the case, then if I were to draw this same kind of picture here, we can add some stuff to it. So if that's the case, then if I were to draw the perpendicular bisector, it would go through that point P. So if I drew the perpendicular bisector here, it would be going through point P. All right, cool. So those are kind of our two theorems that we have, and here's how we're going to use them. For example, on this one, it's wanting to know what is the distance RT. So that's this segment right here, RT. We want to know what that is. And it gives us some other information here. I know it's not really clear, but this is a right angle. And it also says that these two segments are congruent. So if that's the case, that means that this is the perpendicular bisector, or TS. So not only do we know that this is going to be 14 then, these two segments would both be 14, we also know because of the perpendicular bisector theorem that if this is 16, this will also be 16. So that means that RT is 16. Cool. All right, well, we can do something similar here. If we know, in this case, we're looking for AB, this distance right here. And we know that this is 2.5. I'll make that a little bigger because it's kind of hard to see. And then we are also told that this distance is the same as this distance. So this is going to use the converse of the perpendicular bisector theorem. Because if I know that this point is equidistant from A and B, that means that this is the perpendicular bisector. So that means that these would both be 2.5. And then the whole thing, 2.5 plus 2.5, is 5. All right. So that's kind of the simpler version of these two things. Now we're going to step it up just a little bit here over on the third one. First off, we know that this is the perpendicular bisector because it's got the little right angle marker, and these two segments are equal. So that tells me that this one, which is supposed to say 3x plus 1, this 3x plus 1 right here, is going to be the same distance as this. Gosh, is that an 8 or a 3? Goodness, I think it's a 3. 5x minus 3. I know that that's going to be the same as this distance here. So with two things that are equal to each other, we can set them equal. 3x plus 1 equals 5x minus 3. So we'll go ahead and solve for x. So plus 3 on both sides. Minus 3x on both sides. We get 4 equals 2x. And then we divide by 2. So we get that x is 2. But we were not asked for x. We need to find x in order to find what we're asked for, which is hj, though. Hj is this segment here. I need to go back and plug in x to this 3x plus 1. So 3 times 2 plus 1, which is 7. So my full answer here is 7. Okay. try and focus this a little better. Well, maybe that helped. We'll see. All right. So those are ways that we can use the perpendicular bisector theorem and the converse of the perpendicular bisector theorem. Okay, so the last thing we're going to talk about here today is the circumcenter theorem. So the circumcenter is that thing that we constructed back at the beginning of the lesson on the back of our packet. Okay, so that's that place where all the perpendicular bisectors meet up. It's called the point where they are concurrent. So where three perpendicular bisectors intersect, that's the point that they are concurrent at. And that point of intersection is called the circumcenter. All right. And the circumcenter theorem says that the circumcenter of a triangle is equidistant from the vertices of the triangle. So what it says is that if this is the circumcenter, then all three of these segments are the same length. And we know it's the circumcenter because either you could be told that it's the circumcenter, or you could see it in the markings on the picture. We could notice that this is perpendicular and it's bisecting this side. This is perpendicular and it's bisecting the side. This is perpendicular and it's bisecting the side. So if that's the meeting point of all three perpendicular bisectors, that's another way we can know that it's the circumcenter. Or you could just be told it in the problem. Or you could be told that these are all perpendicular bisectors. Either way, we know that down here in this example, this point D is a circumcenter. All right, so there's a lot of things that we can know about this picture just from knowing that this is the circumcenter. For example, we'll know that these all divide the side into two equal pieces. So these are the same, these are the same, these are the same. We'll also then know that this distance from the circumcenter to the corner is the same as this distance, which is the same as this distance, which is a lot of things to mark on the picture, but those are all the things that we know if we know this is the circumcenter. Okay. So now knowing that, I'm also going to make these a little bit clearer. This is 16. This number is 19. This number is 17. And this number is 15. Make those all a little bit bigger. Those were numbers that were given to us. They were just a little bit blurry on the screen. Okay. So now we want to know what is DG. So the distance from D to G. Well, this is one of these from the center to the vertex, and those would all be 19. So DG is also 19. All right, cool. EK, that's this one right here. Here's EK, and it's marked as being the same as this one because it's a perpendicular bisector. So EK is 17. FJ, that's the one right over here. It's half of FG, this whole thing. This one was 15, so this one will also be 15. All right, at this point, I would encourage you to pause the video for a second and see if you can figure out what DE is going to be. All right, hopefully you took a moment and paused the video to figure out DE. If you want to check your answer here, DE is this distance. It's another one that goes from the center to the vertex, just like DG and DF. And those were all the same. They were all 19. So if you said 19, you are correct. All right. And that's pretty much all there is to the perpendicular bisector and circumcenter theorems. So we're going to practice that a little bit with the homework today on the next couple of pages. And then tomorrow we'll end up talking about angle bisectors and incenters and what that does and what that looks like. All right. So if you have any questions, feel free to ask. Otherwise, good luck. Have a great day. See you later.